Yeah, accesses to a hash table are worst case linear, and you can pull some tricks and make them less than linear worst case accesses. How do you do that? Remember the hash table discussions from the second week of class, or whenever it was? Yeah, you can grow height balanced trees off the hash table buckets, and then it won't be quite linear. Worst case, it'll be what? Log. But that's still log, and you have to do n of those. So if you're not careful, it's going to take n log n, worst case. And if you're going to spend n log n time, you might as well just sort and be done with it. That's even simpler. So that's a good try. In practice, it'll work in average case linear, but the worst case is still n log n. So let's try to beat that too. Yeah. Yeah, he's saying group it in groups of two. Let me give you a hint. Hold that thought for a second, because that's a good idea. Let me give you a hint on a much simpler approach. You use an algorithm that we've seen before as a subroutine. Which algorithm have we seen before that runs in linear time, uses a subroutine that will pretty much solve this problem? If I tell you which algorithm, it'll be obvious. So see if you can figure it out. That's a big hint. We've seen a bunch of algorithms already. Some, a lot of them ran in linear time. Let's use one of them as a subroutine here to just knock off this majority problem pretty easily.
Is it
Median, he says median. How many say, yeah, median is onto something with the median? All right. Anybody want to explain his answer, median? He's right. That's a good idea. Why median? How is the majority related to the median? If it exists. The median is the majority. And if it's not quite the majority will be right next to it. But really, let's assume there's an odd number of elements for a second. Otherwise, the median is, maybe the sum of the middle two, but, or the average of the middle two. But let's say it's an odd number of elements, like 101 or 1,000,001 or 1,000,000,001. I mean, you can see that the majority, if it exists, is also the median. Yeah. And how fast can we compute the median? Linear time. Remember that complicated algorithm with the double recursion by 5 authors, several of which were Turing Award winners? I mean, that's what it took to find the median in linear time eventually, after decades of trying. Well, once you have that subroutine, compute the median, and then how do you find the majority, if it exists, from the median? Compute the median, and then what? What do you do with the median? Could you just report the median as the majority and walk away? How many say, yeah, you could do that? How many say, no, it's not quite that simple? So what do you have to do extra? Check. One word, check, count. See if that median actually is a majority, because the median always exists. There's always a median. There's not always a majority. So count how many equal to the median, and if more than half are equal to the median, that was the majority. What about the cases of two majorities? The median just gets reported one thing. So there can be two majorities if, let's say you have 100 elements, 50 is a majority, the other 50 is also a majority. So, because it's greater than or equal to n over 2, right? In the problem specification, we said greater than or equal to n over 2. So technically, you don't need n over 2 plus 1. N over 2 is sufficient to have a majority. So you can have two majorities. So once you have the median, see if it's a majority. If it's not a majority, and if it is a majority, see if there's another majority. How would you test the case where there's another majority besides the one that is the median that you got reported out of the median subroutine, the linear time median subroutine? How do you get the other median? The other majority, if it exists? Not that hard at this point. Pretty straightforward. Yeah, take one of the other elements, it's not the median, and see if there's n over 2 of those, and if there are, that's a majority also. If not, there is no other majority besides the first one that you already counted out to be a majority. Which element are you going to take out of the other half to test for being a second a majority? The one closest to the median? You could do that. But there's even a simpler approach. If there's a second majority, which element out of the other half do you have to test? Any of them. How many can see that? If there is a second majority, all of them are that second majority. So take any of them you want. It's even simpler. Or you can do the one next to the median, but might as well take some random one because that's easier. Okay. So that's finding the majority in linear time if it exists. Now let me show you a much simpler algorithm than that, because a median subroutine is a heavy-duty, double recursive, very high constant linear time algorithm. And so it's a misnomer that it's linear time and therefore efficient. It's a huge constant, and it's complicated, it's hard to implement. I'll show you a much simpler algorithm. And to see this algorithm, think about the elements. So let's say you have a majority of green ones and a minority of red ones. I'm just denoting them by X's and O's, color-coded. And by the way, the algorithm we just described, find the median and then check to see if the median is a majority, and then check to see if there's a second majority. It makes a very basic and fundamental and somewhat restrictive assumption. Because if the objects I'm trying to find the majority of are not well ordered, like if they're pointers or if they're graphics objects or if they're complex numbers or if these objects are matrices, how do you sort a bunch of complex numbers? How do you sort a bunch of matrices? How do you sort a bunch of animals or vegetables or minerals? Majority is still defined for all these classes other than numbers. How many can see that? It's just how many of that type equal to each other? There are. And if there's more than half, then that's a majority. Republicans and Democrats could have a majority of one or the other, or independents or anything else. But these sets are not well ordered, so you can't sort these sets in a natural way. There may not be a total ordering defined even on the set, much less something that you can easily compute. This algorithm I'm about to show now is not only simpler, but will work just based on equality or inequality, not based on total ordering. So sorting may not even be defined here, but there's still a majority here, and it will be found. And it'll happen in linear time, and it's pretty simple. So that's a total order. So that solves the second problem that I posted way back in the slides. Do the majority in linear time, but this time, don't rely on total order. Just use equality or inequality, not greater than or less than relationships. So sorting isn't even defined, and median, therefore, isn't defined either. So you can't use the median subroutine anymore in this scenario, because things are not just greater than or less than. That's undefined. They're equal to or not equal to. That's still defined. So median is useless now. All right. Let me ask you the following question. Let's say there was a majority here in this set. And I take a pair of elements that are unequal. One of them is an X, one of them is an O. And I remove them from the set. I throw them out. What can you tell me about the remaining elements in the set with respect to majority? If I take out an unequal pair, what is true still about the majority in the original set? Unchanged. How many can see that? Yeah, if there was a majority before, now take out two different elements out, that majority that was there before is still the majority there now. If it existed to begin with. If a majority didn't exist to begin with, and I took out an unequal pair, that may screw things up a little bit. Whatever remains all of a sudden can become a majority. But if there was a majority before, it remains invariant, unchanged, by taking out an unequal pair. So it's not an if and only if, it's just if I take out an unequal pair, the majority did not change. If it existed to begin with. If. Okay. Well, that suggests an algorithm right there. What's the algorithm now? So this is an insight. It's not a trivial insight. Happens to be true, but it's called an invariant. In general, an invariant is something that doesn't change. That's why it doesn't vary. It's an invariant. It doesn't vary. It's a property that when you hit something with some operation, the property is preserved. It doesn't change. All right, so removing an unequal pair preserves the majority if there was a majority there to begin with. So what's the algorithm now? We're not done. This is just an interesting insight, but I'm telling you that based on that, you can solve the rest relatively straightforwardly. Yeah. Another object? Oh, you want another object in there? Okay. That's always good to make it a little more general. One, two, three, four, five, six, 7, 8, 9. And let's keep the circle a majority. But now there's a couple of triangles too. Yeah, so the green circle is the majority. So what you want is to remove unequal pairs. If you can find a pair that's unequal and throw it out, the majority element didn't change if it was there a majority to begin with. So that's an invariant. Now the question is, how do you remove an unequal pair? How do you find an unequal pair so that you can remove it? Once you find it, it's easy to remove. Let's say they're all sitting in some big array or whatever, some data structure. So if you just take the first two elements in the array and they're these, you can just remove them and the problem doesn't change. And if you take these two elements and remove them, the problem doesn't change. And if you take these two elements and remove them, the problem doesn't change. But there's an issue here, right? How you guarantee to find two elements that are different? What if you take two elements, like the first two elements of the array, and they happen to be the same? You can't throw them out. And if you put them back into the array, you haven't reduced the size of the problem, and you just wasted some time, and the problem size did not decrease. But there's something you can do. So if you can find in constant time a pair that's unequal, you can remove it, and the problem size decreases by 2. So you spent maybe constant time, hopefully constant time, to find an unequal pair, remove it, and the problem size diminished by 2, which means if you keep spending constant time for every pair that's unequal and remove them, eventually the problem in linear time will vanish to a very small size, and then you'll have your answer. But how do you do that in constant time per pair and avoid cases where you take out a pair and they're the same? They're both green circles. What do you do then? You say pick one of them and throw the other in. You have to be a little careful. Um, Here's what you can do. You can say, okay, if I take these two guys and they're both green, and I look at them and they're both green, I can combine them into a single piece of paper. And now this single piece of paper will have a multiplier of 2x. So I'm saying this piece of paper now will have a multiplier of 2 on that. So you it's basically what you're saying is to throw one back in, but you're throwing both of them back in, but combined into a single object. Okay, and next time you pick an element, let's say these two, and they're unequal, you can throw them out. But if you pick two elements that are equal, you can put them in with a multiplier. Now let's say the two elements that you pick are this one with a multiplier of 2, and then this one of these black triangles. What if you pick this pair now? So each guy now in the set will have a multiplier, and this has a multiplier of 2. If you pick this dark triangle and this double green circle, what do? One of them will cancel out the triangle and be thrown out, and the other one, without the multiplier of 2, just multiplier of 1, will be put back in. How many can see that? So you've done a virtual cancellation. Yeah. And what if you take one with a multiplier of 7 and one with a multiplier of 5? And they're both different. Just the two multipliers are 7 and 5. The 5 will cancel against the 7, yielding 2, and the 2 goes back. And you've canceled 5 simultaneously. And if you pick two that are the same, you took 2 pieces of paper and returned 1 piece of paper with a multiplier of 2, and you're still reducing the problem size by at least 1 piece of paper with every iteration. And now you have a general rule of what to do when you pick any arbitrary pair of objects with their respective multipliers. Some cancellation will happen, or merging will happen every single time. How many can see that? You're not wasting work. You're always making progress now by following this simple rule. Yeah.
So when you cancel from like 7 and 5, then you get 2. But what if there was another that was 4, 7, 5, and 4? Now that 4 one will become the majority instead of the 7.
So far, we're just doing this blindly, and there could be other multipliers. So I'm not saying that all the green ones will be multiplied right there and that set. There could be another 3 green circles over here separate than these 2 green circles. That's okay. If you happen to pick up a multiplier of two green circles and 3 green circles, you combine them into a single set of 5 green circles and put that one back. That's okay. You do that.
No, different ones. I mean 7 circles and let's say 5 of triangles.
7 circles and 5 triangles. 5 will cancel the 5. 5 circles will cancel the 5 triangles. Those will go poof. And back in, you will put in the 2 circles as an element.
But what if there were 4 triangles also? And you just looked at the starting.
You're asking what if there were 4 triangles? Where are the 4 triangles?
Basically you have
Se-
3 multipliers.
Yes.
So 7 are circles, 5 are axes,
Yes.
and 4 are triangles.
Oh, we just pick up arbitrarily one pair of objects. We do the either merging or cancellation. We put it back. We only worry about the other ones in future iterations. So there could be many sets of multiplied triangles. There could be 5 triangles here, 3 triangles there, 2 triangles there. We don't worry about all of them in one fell swoop. We take 2 pieces of paper, 2 come out, and 1 goes back in at most. That's one operation. Doesn't matter what else is true about the set. Those will be taken care of in future subsequent iterations. Those will get canceled too eventually. So what we're doing is taking 2 pieces out, either merge them if they're the same object, or cancel them against each other if they're separate objects, and whatever left over after the cancellation, if any, that goes back in as a single piece of paper with a multiplier on it. So 2 pieces of paper come out, 1 goes in. It's like the inverse of Thunderdome. 2 people come in and 1 comes out. How many even know what I'm talking about? Okay. Mad Max fan. Okay. So with every iteration, 2 pieces of paper are leaving and 1 goes back in. Guaranteed. At most 1, because both of them may disappear. But at least 1 less piece of paper is there with every iteration. Now, which 2 pieces of paper are you going to pick at every iteration for this to work? Which 2 pieces of paper? Do you need to specifically find 2 different ones? No, because if they're the same, you merge them. Add the multipliers, put that back in. Do they have to be something with a multiplier of more than 1? No, any multiplier will do. So which 2 pieces of paper do you take out at every iteration? Any. Take the first 2. So now you can really implement it as an array. You have an array of these objects. Take the first 2. They either merge or they cancel, and at most 1 goes back in, and now the array is 1 less. Then take the first remaining 2 in the array, and keep going. How many see this algorithm now? Okay. A couple of loose ends. Let's say you take everything out, and at the end, there's 1 lone object left. Let's say we took these 2, and they canceled. Then we took these 2, and they canceled. And then we took these 2, and they canceled. And now that's the only one left. What do you do now? Is this the majority automatically? I mean, say, yeah, that's a majority guaranteed. I mean, say, not so fast. Why not? Yeah. You got to check it. Because this process will work and cancel everything against everything else, whether there's a majority or not. See, all the elements are unique. They're all unique, unequal integers. Or objects, not solely integers. This cancellation will happen over and over and over, and there will be 1 left. But it's not the majority. Not only that, there is no majority. Not only that's not the majority doesn't even exist. So when you have 1 left at the end, you better check it. How do you check it? How fast? What does it mean to check it? Count out how many times that object actually appears in the original list. That's linear time, obviously. And then you'll know if it's a majority or just whatever's left over that's not necessarily a majority. Because remember, we said that once you eliminate a pair that's unequal, the majority that's in the set, if there was a majority to begin with, doesn't change. Let me put it more simply. The majority doesn't change if you eliminate an unequal pair if there was a majority there to begin with. But that's an if. That's a conditional. If there was no majority there, the majority doesn't change either. Because there was no majority there before, and there's no majority there after. But doesn't mean what's left over at the end of this process will be a majority. It doesn't have to be a majority. It could be a non-majority, because the majority may not exist. Question?
What if we remove one green and we have only 6 of pairs? If we are removing the unequal pair, then there is nothing.
Yeah, so if you remove unequal pairs and you have left something that's a non-majority, you're saying? Okay, so let's sort of do what you're suggesting. So 4 green, okay. Very, very good point. I should give you extra credit just for asking that. All right, let me paraphrase what she's saying. She's saying, what if you remove unequal pairs? So let's remove this pair first, okay? Then we remove this pair, okay? Then we remove this pair. And finally, we remove this pair. And there's nothing left, right? Very good. We know what extra credit. Submit that to the class website. That's a very good insight. That's a boundary condition. How many, first of all, see that can happen? The majority could be eliminated by successive cancellations against other things that are not equal. Okay, so what do you do? Wait, let's not be so hasty. There is a majority there. Remember, majority is n over 2 or more. So out of 8 elements, if 4 were the same, that's a majority by definition. So there is a majority. It just got canceled out in this process, and now there's nothing left. So what do?
We can stop at if we are left with one or
Ah, so don't wait till the very end when it's empty, but instead do what? Yes. Leave the last 2 elements. When there's 2 left, don't cancel them. Instead, check those for being the majority. And if there was a majority, the last pair standing will contain that majority. Because that majority was enough to cancel every other thing, and it will persist till the very end by this invariant. Right? So that last pair, leave alone, check both of them for being a majority, and either one of them will be the majority, in this case the green guy, or both of them will be the majority. If there's 2 majorities, they'll both persist to the very end. The last pair standing will contain both majorities. How many can see that? Yeah. So excellent point, easy to fix. What else? Anything else? Is there any other loose ends? So when you implement something like this, yeah, go ahead. Yeah, so another excellent point. So he's saying there's 2 last pieces of paper ending up in the set. Don't necessarily have to have a multiplier of 1. They can have a multiplier of greater than 1. You can have one piece of paper labeled with 7 circles and another piece of paper at the very end labeled with 7 triangles. And now you're trying to cancel 7 against 7. But so we have to kind of generalize that solution to not just the last 2 elements, but the last 2 pieces of paper with multiple elements on each, with a multiplier. But either way, it's the very last pair of multiplier elements with multipliers. So if you have 7 left and something else, one of those 2 will be the majority or both will be the majority, if the majority exists. Or neither may be the majority. But that's the only 2 things you have to check. Yeah. Yeah. There may not be a majority. Yeah. That's why you have to check. You have to check both. So maybe 0 majority, 1 majority, or 2 majority. Okay, so when you implement something like this, now, do you really have to take it out of the array, look at them, do the cancellations, put it back into the array, and do it like that literally? No, you don't. What can you do? Take the next one. So basically, have all these guys there, and have an extra variable that holds, one of them, and you take the next guy in the array. If it's the same, you eliminate it. If it's equal, you have a multiplier now in your hand. If it's the same now again, the multiplier clicks up. If it's not the same, the multiplier clicks down. So all you need is this variable, that's my hand. And you take every element now into my hand and either clicks up the multiplier if it's the same as the element that I have in my hand. If it's different, I click down the multiplier and it gets eliminated. You see what's going on? So I don't even have to take 2 out and put 1 in. I just take 1 out at a time, have this constant variable in my hand that's the latest element. And if something gets eliminated with a higher multiplier, the type of object in my hand gets to be that other object with the difference in the 2 multipliers now instead. How many can see that? So when you implement, it's even simpler than having an array and putting papers ins and out. Paper is just, it's not even papers, it's elements coming out. The multiplier is really just in my hand as an extra integer multiplier of the object that's in my hand that's the type of the ones that I'm keeping track of. So in that scenario, when does this end? How does this end? When I have how many elements left? Essentially one in my hand and one in the bag, or one in the array. Or maybe none in my hand and two in the array. Either one, that last two elements that you have either in your hand or in a bag or just in a bag or just in your hand, just check those for majority. So the implementation is even simpler than that. How many lines of code are we talking about now to implement this with this one extra variable and one extra multiplier? And the array is just the input array, which I don't even have to modify at this point. The input array is just constant, it's fixed. I just step down the array and do the cancellation in that variable I have in my hand, and the other hand I have a multiplier. How many lines of code are we talking about, roughly? 10, 8, 7, 12, it depends on the language, but very few lines of code. One loop, and an if statement and a couple of assignments, and that's the end of it. How simple is that? And it doesn't rely on sorting. And it sure as heck doesn't rely on median finding with double recursion and all this giant overhead constant, and look how simpler it got. Because with the median finding algorithm, if you have to unroll that into a large piece of code, I mean, that's hundreds of lines of code to find the median, plus a huge constant. So you see how, you keep refining the algorithm more and more, and as you refine it, it gets simpler and simpler, and also more efficient, hopefully, and also less lines of code, and also more foolproof, because if you have just 5 lines of code, there's not a lot of places where errors can hide. Truth is just staring at you in the face. It's beautiful, it's elegant. Right? Bugs have no place to hide in just a few lines of code. But if you have hundreds of lines of code, there's a lot of bugs in there, most likely. So that's another beautiful algorithmic design. My gift to you. Any last questions? All right. See you next time.
它是2分之一，可以。最基本的是